In this video, we're going to look at a specific ring homomorphism and see how we prove that it is a ring homomorphism. So what we're going to do is we're going to let phi be defined as going from the set of integers to the set of integers mod n, and we're going to say that phi is given by the formula that phi of any integer k is going to be equal to r, where k is congruent to r mod n, and of course r needs to belong to the set 0, 1, all the way up to n minus 1, which are the formal symbols of Zn. Now, to show that this particular function is a homomorphism, what we need to do is we need to show that phi preserves both of the ring operations. In other words, we need to show that phi of a plus b is equal to phi of a plus phi of b, where what we know about a and b is that they are integers. And we also need to show that phi of a times b is equal to phi of a times phi of b. Again, where a and b are integers. If we can show this, then we can say that phi is a ring homomorphism. And the way we're going to do this is we're actually going to take a little bit of time and care to talk exactly about what this statement right here really means. So the first thing that I want to do is I want to remember something about the division algorithm. So I want to remind you that if a and n are any integers, then the division algorithm says that a can be written as q times n plus r. And what we've got, of course, in our situation is that we know that a and b are indeed integers, and n is some fixed integer for the ring z sub n. So I know that there do exist q1 and r1 such that a is equal to q1 times n plus r1, and there also exists q2 and r2 such that b is equal to q2 times n plus r2, and the q1, the r1, the q2, the r2 are unique when we insist that the r1 and the r2 both satisfy being strictly less than n and bigger than or equal to 0, that they are legitimate remainders. And under these circumstances, we know a couple of very important things. Since a is equal to q1 times n plus r1, that tells us that a is congruent to r1. Let me get my writing clearer. Mod n, and b being equal to this guy says that b is congruent to r2 mod n, and r1 and r2, of course, are legitimate elements of Zn, and so we know all about how to do the arithmetic in Zn for r1 and r2. There's one more thing that I also want to make a note of before moving on to another page. Because of this fact here, we know that phi of a is simply r1. And because of this fact here, we know that phi of b is equal to r2. And we're going to use this to show that phi does preserve the ring operations. So now let's look at this. First of all, I want to think about what happens in Z. I know that A plus B is going to be Q1 times N plus R1 plus Q2 times N plus R2, and that can be simplified to Q1 plus Q2 times N plus R1 plus R2. And so what I do know is that A plus B is congruent to R1 plus R2 mod N. And that says that phi of A plus B is going to be R1 plus R2 when we are inside Zn. And of course, inside Zn, the arithmetic takes care of itself, and that R1 is phi of A, and that R2 is phi of B. And when we put this together, we have phi of A plus B is indeed phi of A plus phi of B. And so we can say phi preserves addition. Well, we have to do the same thing for multiplication, and it really isn't any harder. In Z, we have A times B will be equal to Q1 times N plus R1 times Q2 times N plus R2. And when we distribute that out, we're going to get Q1 times Q2 times N squared plus Q1 times N times R2 plus R1 times Q2 times N plus R1 times R2. And what I want to notice is that we have an N that can be factored out, and when we factor that N out, we're going to have Q1 times Q2 times N plus Q1 R2 plus R1 Q2 times N plus R1 times R2. And this is A times B. And that says that A times B is congruent to R1 times R2 mod N. And so phi of A times B will just be whatever R1 times R2 is in Zn. And of course, that winds up saying that phi of A times B actually winds up being phi of A times phi of B, because this R1 is phi of A and this R2 is phi of B. And once we have that, we have everything that we need. So phi preserves multiplication as well as addition, and that's enough to conclude that phi is a ring homomorphism from the ring of integers to the ring Zn.